In section 3.4, we're going to talk about two very kind of broad and general derivative rules. It's not going to be how to find the derivative of one function in particular, but how to find derivatives of functions that I guess have a particular pattern, or when you see particular operations. So obviously you can see from the title, when we have products or quotients in our function, we have to use a special rule. In section 3, we said that if our function had addition and subtraction in it, we could just take the derivative of each piece individually, but that is not true when pieces of our function are being multiplied and divided. So just as a quick little review, recall that when we want to take the derivative of two functions that are either being added or subtracted, you are allowed to just find the derivative of each piece individually. This is only true for addition and subtraction. It is not true for multiplication and division. There are completely separate rules for how to handle multiplication and division, and that's what we're going to talk about in this section, the product and quotient rules. So the derivative for f of x times g of x is not equal to f prime times g prime. You cannot just take the derivative of each piece if it's multiplication. And I'm not going to write it down, but likewise, if that was f of x divided by g of x, you cannot just take the derivative of each piece. We've got a special rule we're going to need to use instead. So let's start with the product rule, and then we'll go on to the quotient rule, and we're also going to look at some problems where they're kind of mixed together. And I'm going to give you a suggestion on how to keep this nice and organized in case we see some more difficult problems. So this is going to help us figure out how to take the derivative of a function that contains a product of input variables. And typically we use x, but it doesn't always have to be. Another common variable that we're going to see for our independent variable is t. So we're not going to do these derivatives yet, but just a couple of quick examples of what I mean by functions whose contains products. F of x equals x times e to the x. This is a product of two functions of x. And what I suggest you do, and one of the things we're going to do when we start working these, is you identify what two things are being multiplied here, and you will see that both of them have x's. So it's a product of two functions of x. So we're going to have to use a special rule to take the derivative. Another example. Two x minus 5 times the sine of x. Now we haven't talked about trig functions yet, and we're still not going to talk about them in this section, but we will very, very soon. And this is a product of two functions of x. Now 2x minus 5 already has parentheses around it, and if we put our own separate parentheses around sine x, that is a product, and the two things that I have my parentheses around both have x's in them, so it's a product of two different functions of x. Now sometimes you might be able to do some algebra to fix that, and if so, that's great. Go ahead and do the algebra to fix it. Like if they're both just linear polynomials, you might just be able to distribute and turn it into a quadratic and then find the derivative term by term. But a lot of times you won't be able to do anything like x times e to the x. There's nothing you can do to rewrite that so it's not a product. It's going to have to stay that way. One more really quick. The square root of x times x squared plus 3x. So we could, if you want to, put parentheses around our square root. Sometimes it makes it a little more obvious that we've got two separate functions of x being multiplied together. Now this one we could fix with some algebra, and we could potentially, by doing some algebra ahead of time, make it so we don't have to use the product rule. But if we don't recognize that, or if we are not very confident in our algebra skills, we could work it out as a product rule problem, and we would get the same answer. So these are all examples of things that we are going to learn how to find derivatives of in this section when we've got a product of two functions of x, and we want to find the derivative. So there's a formula that we need to remember. And this formula is extremely important. Anytime we want the derivative for f of x times g of x, so these are just two random functions of x, we're going to pair up the derivative of one of them with the original of the other. And I like to start with the derivative of my first one because that is the pattern we're going to see with our quotient rule. So I do the derivative of the first times the original of the second. And then plus, and then I flip-flop it. Original of the first, derivative of the second. So in order to work out these problems, it's good to identify at the very beginning what is your f and what is your g. And work out their derivatives. And then all you have to do is just kind of assemble this little formula to get your answer, and then maybe do a little bit of simplifying. So we're going to identify f and g at the very beginning of the problem, and we're going to calculate f prime of x and g prime of x individually. Then it's just a matter of kind of putting the puzzle pieces together and simplifying. So let me show you how this is going to work. So again, for product rule, we do the derivative of one multiplied by the original of the other. And we do it both ways with addition in between. So f prime g plus fg prime. So this is extremely important. And if you're going to go on to take any more calculus classes, this is just going to be something that you are just going to expect to know off the top of your head. It's just going to be second nature, and you're going to do it a lot. So if we want to calculate the derivative for x squared times e to the x, We are definitely going to need the product rule on this because I've got x squared times e to the x. I'm multiplying two functions of x together. So what I like to do ahead of time, off on the side, I'm going to identify which piece is which. And really with product rule, you get to choose. So I'm going to say f of x is my x squared, and g of x is my e to the x. And in order to write out my answer, I need the derivative for each piece. So f prime, now in section 3, we learned how to do the derivative for x squared. We have to use the power rule. So the derivative for x squared is 2x. And we also learned the derivative for e to the x is e to the x. And we've got all the pieces we need. We just need to remember the pattern to put it all back together for product rule. So product rule says you're going to do f prime times g. You're like going to crisscross here. So I'm going to do f prime g. So 2x e to the x plus x squared e to the x. And that's it. That's our derivative. That is the derivative for x squared times e to the x. Now, this one is one that we could possibly fix with algebra. Once you see it, though, depending on how confident you are with your algebra skills, you might not want to. It might take a lot of extra time that we really don't want to mess with. So we want to take the derivative of x squared minus 1 times x to the 4th minus 5x cubed plus 9x squared plus 3x minus 2. It's definitely a product of two functions of x. We can see our two functions here being multiplied together. But there really isn't anything preventing us to going ahead and multiplying them out and getting this written term by term, except for the fact that it's going to take quite a while. It's going to be gigantic. And because there's going to be so many steps, there's a lot of room for error. So it might be beneficial for us to just go ahead and start the derivative process and not really worry about that algebra stuff right now. Once we do the derivatives, these functions will actually be easier, and then the algebra will be easier. Because remember, the power rule is going to make all these powers go down. So our f of x is x squared minus 1. Our g of x is x to the 4th minus 5x cubed plus 9x squared plus 3x minus 2. And we want each of their derivatives. F prime of x, well, the derivative for x squared is 2x. The minus 1 is a constant, so its derivative is 0, so we don't write anything. You don't write plus or minus 0. And then for g of x, we've got this really long polynomial, but we just do the power rule on each piece. So we're going to get 4x cubed minus 15x squared plus 18x plus 3. So that's all the pieces that we need to do our derivative with product rule. And then we crisscross. And I like to start with f prime in my answer because that's the pattern we're going to see when we do quotient rule. It's just nice to be consistent. So I'm going to do f prime times g. So 2x times x to the 4th minus 5x cubed plus 9x squared plus 3x minus 2. So that's the derivative of my f times my original g plus my original f. So now I'm on this one. My original f times my derivative of my g. This multiplication is definitely easier because I just have to do distributing. This one is a little bit easier because it went from a 4th degree polynomial to a 3rd degree polynomial. And most likely we are going to be asked to simplify this as much as possible. At some point we're going to be doing more with these derivatives besides just finding them. We do want to show you that there are things that these derivatives are used for, and leaving them in this format is not very helpful. So we're going to want to simplify this out to like a nice standard form polynomial. So technically we have found the derivative. We've got f prime g plus fg prime. This is the derivative, but we want to clean it up a little bit. So I'm going to go ahead and distribute my 2x into every term here in the first part. And then for the second part, we're going to have to FOIL out because this is a binomial. So we're going to have to do x squared times everything and then -1 times everything. And we're going to have a lot of terms to put together at the end. So I'm going to move my equals back a little bit. So with my 2x, I'm going to have 2x to the 5th minus 10x to the 4th plus 18x cubed plus 6x squared minus 4x. So that's just distributing 2x into my original g. And then for the second part, I need to distribute x squared into my g prime. So that's going to make all the powers go up by 2. So I've got 4x to the 5th minus 15x to the 4th plus 18x cubed plus 3x squared. And then I need to distribute -1 to all of them, which is just going to change all of their sign. So minus 4x cubed plus 15x squared minus 18x, and I'm running out of room. Let me see. Minus 18x minus 3. And there's lots of stuff here that we can put together. So one more step and we will have our final answer. So I've got multiple x to the 5th terms. Well, 2 of them. So I've got 2x to the 5th and 4x to the 5th. That combines to make a 6x to the 5th. And then I've got minus 10x to the 4th minus 15x to the 4th. Makes a total of minus 25x to the 4th. And then plus 18x cubed plus 18x cubed minus 4x cubed. That's going to be a plus 32x cubed. And then plus 6x squared plus 3x squared plus 15x squared is a plus 24x squared. And we've got minus 4x minus 18x is a minus 22x. And then we've got our little minus 3 there at the end. So if we needed to actually use this derivative for anything, we would definitely want to have it all multiplied out. All of our next chapter, chapter 4, is going to be applications of derivatives. And one of the things we're going to have to do is set it equal to something. And we wouldn't want to solve it where part of it's factored and part of it's not factored. And that would be really tough to solve in that format. So this is going to be the final answer for my derivative. And I want us to look at one more, but in this one, we're going to find the second derivative. So remember, if you see a little superscript, it's not an exponent. I don't want you to raise it to a power. This is a superscript, meaning second derivative. We want to find the second derivative for and a lot of these, unfortunately for right now, could be fixed with algebra until we learn a few more rules and until we learn our trigonometry, which is just a couple of sections away. Let's do 2 e to the x square root x. Now our goal is to get to the second derivative, but remember, you can't jump straight to the second derivative. You have to do the first derivative first. And then once we have our first derivative, we'll just apply all of our derivative rules again. So this is definitely a product of two functions of x. Now what you do with the two is completely up to you, but what I like to package it with one of my functions. That way I don't forget about it at the end. So I'm going to say my f is 2e to the x, and my g is square root x. And that's how I'm going to start doing my first derivative. So f prime. Now 2 is just a coefficient, and we learned in section 3 that coefficients just get carried on to the answer. The derivative for e to the x is e to the x. G is going to need a little bit more work because we're going to have to rewrite square root x as a power of x so that we can do power rule on it. G prime is going to be 1/2 x to the negative 1/2, because remember, power rule says bring the old exponent out front as a coefficient and then subtract 1 to get the new exponent. So we get 1/2 x to the negative 1/2. And I'm not going to simplify that or rewrite it yet until we get to our final answer. So then crisscross for your product rule. My first derivative is f prime g, so 2e to the x square root x, plus fg prime, so 2e to the x times 1/2 x to the negative 1/2. That's the first derivative. Now there isn't anything I can do to simplify that first term, but that second term I am going to go ahead and cancel off the 2 times 1/2 because 2 times 1/2 is just 1. That'll make my second derivative a little bit easier. So this is 2e to the x square root x plus e to the x times x to the negative 1/2. Now again, I didn't rewrite x to the negative 1/2 yet because I'm not done with the problem. Now, if I was going to submit this as an answer, I would want to rewrite x to the negative 1/2 a little bit nicer. And we would rewrite that as just this part. Negative 1/2, the negative means it wants to go to the denominator, and the half means it's a square root. So just that second term would really be e to the x over square root x. Just the second term. But we're not done, so I'm not going to do that yet. We want to go on to the second derivative. And this is going to be kind of tough because we've got two separate terms here. See, there's a plus. That means we can deal with these derivatives separately. I can do the derivative of the first piece and then just put a plus sign and then do the derivative of the second piece. The problem is, though, each of them individually is going to need a product rule. So I'm going to have to do product rule twice in order to get my second derivative, which is fine. It's good practice. We just have some work to do. So my suggestion is do one of them at a time. So I'm going to work with my first piece, and I'm going to say f in the first piece is 2e to the x. So notice I'm not going back up to my old f and g labels. We are now like working with a brand new problem. This is our new function here, and we need its derivative. So my first term has to be dealt with like a product rule. So in the first term, I have a f times a g. So my f of x is going to be 2e to the x. My g of x is going to be square root x, which we just said a minute ago is going to have to be rewritten as x to the half. We need the derivative for each piece. And then we can write out the derivative for our first term. It's f prime g, 2e to the x, square root x, and then fg prime is 2e to the x times 1/2 x to the negative 1/2. That is the derivative of the first term. And now I'm going to go over and do the derivative for my second term. So I'm going to let e to the x be my f of x, and I'm going to let x to the negative 1/2 be my g of x. To do the derivative with the product rule, I need each of their individual derivatives. The derivative for e to the x is e to the x. The derivative for x to the negative 1/2, we're going to do the power rule on. The old exponent comes out front, and we subtract 1 to get the new exponent. And then we set our pattern back up. We do a little crisscross here. And this is just going to be combined with addition to what we've already done. We just transfer that addition down. So I'm going to do f prime g, which is going to be e to the x times x to the negative 1/2, plus fg prime, which is e to the x times negative 1/2 x to the negative 3/2. So that's a really big answer. We're going to simplify it just a little bit, do some algebra things that hopefully make sense. We saw earlier the 2 times the half is just going to equal 1. Anywhere we have an opportunity to change a negative exponent by moving it to the denominator, we're going to do that as well. Any fractional exponents, we're going to change back to radicals as well. So the first piece is perfectly fine, 2e to the x, radical x. The second piece, x to the negative 1/2 means square root in the bottom. Now the e to the x does not move. It does not have a negative exponent, so leave that alone. It's just the x that goes down. Ooh, the second piece is also e to the x over square root x. So we really have 2 of them. And then the last piece, we've got this times negative 1/2 here, so I'm going to change it to subtraction. And then we've got an x with a negative power, which means it wants to be moved down, so we're going to have a fraction here. The e to the x does not have a negative power, so it stays in the top. The 1/2 is going to put a 2 in the bottom. And then we've talked about this before. When we move down that x to the 3/2, the denominator portion of that exponent means a square root, but the numerator portion remains a power, x cubed. And there's probably some more algebra things we could do, but those are the main ones. Those are the main ones. Combine like terms, rewrite negative exponents, rewrite radicals. This is going to be the most helpful when we have to continue using these derivatives to do more things in the next chapter. This is our second derivative. And our second derivative does have usefulness as well. We've learned that our first derivative tells us the slope on a graph. And we will learn in chapter 4 that the second derivative tells us something called concavity, which you don't need to worry about right now, but that tells us how the graph curves. So the second derivative is also very helpful. Okay, so for product rule, just a quick little overview before we go on to quotient rule. You have to know this formula. If you're ever asked to take the derivative of the product of two functions of x, you're going to match up the derivative of one with the original of the other. So f prime g plus f g prime. And you need to keep this nice and organized because these problems can get really tricky, especially when I show you the quotient rule. It can get really tricky. So identify your f and your g, take each derivative, and then it usually just ends up, if you keep it nice and organized and written it out the same way, it just usually ends up as a crisscross on who gets matched up with who. And then we write out the product of our crisscrosses there. So again, identify your f and your g, take each of their derivatives individually, and crisscross. So for the quotient rule, part of it is going to look very similar to our product rule. And there's a reason that I do the product rule the way that I do. So if we are ever asked to take the derivative of f of x divided by g of x. Now, quotient rule can even work if the numerator doesn't have any x's in it. Some people like to use quotient rule anytime that you have x's in the denominator, and that's perfectly fine. You can do that. That just means our f of x is going to be a constant, and we'll look at an example of that so you can see. But anytime we're asked to do the derivative of a quotient is the answer to a division problem. We are going to start with the derivative of the numerator, so f prime, and we're going to match that up with the original of the denominator, which is g. Now this is exactly how the product rule started out, f prime g. And then we're going to have f g prime. We're going to flip-flop it. The one difference that we're going to see in quotient rule is there is subtraction between them. With product rule, it's addition between them. With quotient rule, it's subtraction between them. And then quotient rule also is going to be a fraction with g squared in the bottom. So there's two main differences between quotient rule and product rule. Quotient rule has subtraction between those two products, and it also has divided by g squared. Other than that, the pattern you see there in those two terms in your numerator is exactly the same as the pattern that we see in product rule. Fg prime, f prime g, fg prime. So just like we did with product rule, I like to identify what my f and my g are and write out what each of their derivatives are individually, and then just take all of my pieces and put them back together. So if we are asked to find the derivative for 2x over x squared plus 5x. 2x over x squared plus 5x. The numerator is our f of x. The denominator is our g of x. We need each of their derivatives individually. So far, this looks just like our product rule, and it should. We've got all the pieces we need. Now we just need to put it back together with our new quotient rule formula. We're still going to crisscross. We're going to do f prime g. So I'm going to do 2 times x squared plus 5x minus, there's one of the big differences between product and quotient rule is the minus, times fg prime, so 2x times 2x plus 5, all over g squared, your original g squared. That's our other big difference, is that we still have, we've got g squared in the bottom. Now you should always simplify your numerator when you do quotient rule, because there will be usually some easy multiplication and subtraction to do. So we do want to go ahead and distribute here and see if there's some like terms that we can combine. Be very careful though, because technically this minus is going to have to distribute as well. And that's a very common mistake with quotient rule. So this is 2x squared plus 10x minus 4x squared minus 10x all over x squared plus 5x squared. Now you do not need to FOIL out the denominator. You can always just leave your g squared alone in the bottom. Don't need to do anything to it. And we do see that in the numerator we've got plus 10x and minus 10x. Those guys cancel. And then our other two terms are like terms. They can combine. 2x squared minus 4x squared is a negative 2x squared. So this does simplify down quite nicely. We get negative 2x squared over x squared plus 5x squared for our derivative. I'm going to look at another one real quick, and then I'm going to look at a really difficult one that combines our two rules. So this one, we just want the derivative for 3e to the x divided by 2x plus 1. So we have a division problem between functions of x, so we have to use a quotient rule. We can't just take the derivative of each piece individually and say, voila, that's our final answer for our derivative. So with the quotient rule, we always call our numerator f of x, and we always call the denominator g of x. In order to reassemble our derivative, we need each of these individual derivatives. 3 is just a coefficient. It'll just transfer to the answer. The derivative for e to the x is e to the x. And the derivative for 2x plus 1 is just 2, because that's a linear equation. And we need to crisscross these guys. And we start with f prime. So I've got 3e to the x times 2x plus 1 minus 3e to the x times 2 all over g squared. Now, one thing I want you to be very careful of is these do not cancel. You are always going to see a g in the top and a g squared in the bottom, but you cannot cancel them because of that subtraction right there. That original g in your numerator is only part of one of the terms. And you can only cancel between the numerator and the denominator if that factor can be pulled out of the entire numerator. And 2x plus 1 can't be pulled out of the entire numerator. It's only a piece of one of the terms. So do not cancel that 2x plus 1. Also, you do not need to FOIL out your denominator either. We could, though, if we wanted to. I don't think there's going to be much simplifying we're going to be able to do in our numerator, but we could go ahead and multiply that out if we want. So this is 6x e to the x plus 3e to the x minus 6e to the x. So we do have some like terms we can combine. all over 2x plus 1 squared. So these two guys are like terms. We can put them together. So this is 6x e to the x. And then that's going to combine to make a minus 3 e to the x, all over 2x plus 1 squared. So it does simplify it a little bit by multiplying it out. This next example is going to be quite a bit more difficult because we're going to have to combine both of our rules. So we want to find the derivative for, let's say, e to the x times x squared plus 5 over 3x minus 1. So in this function, we see a product in our numerator, but also the entire function itself is a fraction or a quotient, so we have to use quotient rule. So one of the most confusing things sometimes is to figure out whether to do the product rule or the quotient rule, and technically we're going to do both of them, but it might be unsure where to start. So what I want to point out to you is that overall, this function is a fraction. It has a numerator and it has a denominator. So irregardless of what the numerator and denominator are, this function is a fraction. So you need to start with the quotient rule. Now, in the process of doing the quotient rule, some other things might come up, but we're going to start this problem as a quotient rule problem. So I'm going to say my numerator is f of x. So f of x is e to the x, x squared plus 5. And my denominator is 3x minus 1. So I know I'm going to need g prime, and g prime is really easy. It's just 3. But most of my work is going to have to be done here with f prime, because we know to do quotient rule, once we identify our f and our g, we need both of our derivatives. And now this f here is a product. So in order to do the derivative of our f, we're going to have to do product rule. Now you can write it out as a f and a g again if you want to, or you can just remember I've got to do the derivative of the first, paired up with the original of the second, and then plus, and then flip-flop. So that's up to you how you want to write it out. You can write it out as a f and a g again. It might be kind of confusing to have multiple f's and multiple g's, so I really don't suggest doing an f and a g again. If you do, I would change letters and maybe write it s of x and t of x, or m of x and n of x. But overall, we need to get f prime, and we need to do it with the product rule because f is a function of two functions of x being multiplied together. And f starts with the derivative of the first times the original of the second, plus the original of the first times the derivative of the second. And now we can take all of our pieces and put them back together with quotient rule. Remember, we crisscross these for quotient rule. So we always start with f prime, which we just got this giant product rule for. F prime is e to the x, x squared plus 5, plus e to the x times 2x. And that's times the original g. So this is going to have to be in its own big set of parentheses, times 3x minus 1. And then quotient rule has subtraction. And then we want original f times g prime, which is just 3. And then all over the original g squared. And remember, you're going to see a g in the top and the g in the bottom. Do not cancel those unless both terms in the top have a g, and they don't. The original g only appears in that first term in the top. Okay, so just be careful with that. Let's see. This one's pretty complicated. let's see if we simplify it at all, if there's anything that we can do. And I don't suggest you try to do too much of this all at once. Don't be scared of trying to save paper. Saving paper usually does not lead to anything good in math class. So this is e to the x times x squared plus 5, and actually I usually like my e to the x as my second factor. So this is x squared e to the x plus 5e to the x plus 2x e to the x times 3x minus 1 plus 3e to the x times x squared plus 5 all over 3x minus 1 squared. And we could go ahead and distribute all of this stuff if we want. Not too much more work to do to get all that done. So that's going to be 3x cubed e to the x plus 15x e to the x plus 6x squared e to the x minus x squared e to the x minus 5e to the x minus 2x e to the x, and we'll have to distribute that as well, plus 3x squared e to the x plus 15 e to the x, and we do have a lot of like terms we can put together, all over 3x minus 1 squared. So every single term has an e to the x in it. But we'll have like terms if they have the same power of x in the front. So let's start with the biggest power of x. We have x cubed e to the x, and there's only one of those, the 3x cubed e to the x. And then some x squared e to the x's. We've got a few of those. Got quite a few of those we can put together. So we've got positive 6, minus 1, minus 2, and positive 3. So that's 9, 8, 7. So a total of positive 6 of them. So plus 6x squared e to the x. And then some linear x e to the x's. We have positive 15 and minus 5. That's going to make a total of positive 10. And then our little lonesome 15 e to the x at the end that has no x's in the front, all over 3x minus 1 squared. So it is very common for you to have to simplify out your numerator after you've done your quotient rule, but we almost never, ever, ever mess with the denominator because there's really nothing in the denominator except the old g squared. But the numerator is a conglomeration of a whole bunch of stuff. So there's quite a few examples of our product rule and our quotient rule, and even a much more tricky one that requires both of them. So to finish this section up really quickly, there's a couple little tidbits that I want to tell you. This technically should be in a different section, but they cover it in this section and then they do some problems in this section. So when you get to it in your homework, I just don't want you to be too surprised. So the derivative for e to the kx. So k is just a number. Any real number. And we're never going to deal with complex numbers in calculus class. So it could be a decimal, it can be a fraction, it can be a positive, it can be a negative, it could be anything. So we've already talked about the derivative for e to the x is e to the x, but if they decide to throw a coefficient up there on your x, the derivative is going to be k times e to the kx. So that coefficient, you're going to bring it out front the coefficient in your exponent, you're going to bring it out front as a coefficient of your function. But the e function never ever changes. Anytime you do the derivative of an e, it always stays itself. So we still have e to the kx in there, but we've just thrown an additional k in the front. So let me show you an example of some numbers. Sometimes those arbitrary letters in there make it kind of tricky. The derivative for e to the 3x is 3e to the 3x. The derivative for e to the x over 2. Now, the first thing I would do is I would rewrite this. So you could, instead of looking at it as division, rewrite it as multiplication. X over 2 is the same as 1/2 x. And it's a little bit more obvious what you're supposed to do. X over 2 is the same as having a 1/2 coefficient. So this is 1/2 e to the 1/2 x, or x over 2. And if we were to do higher order derivatives, we would just continue to bring that coefficient out again and again and again, and it would just multiply by whatever was already out there. So if we wanted to find d3 dx3 of e to the negative 2x, well, that means third derivative. That means we need to apply our derivative rules 3 times, but we can't just jump straight to the third derivative. We need to do the first derivative and the second derivative first. So our first derivative is negative 2 e to the negative 2x. And then we'll take that answer and find the derivative again. And a negative 2 comes out again. So negative 2 times negative 2 is positive 4. And then we'll take that and we'll do it again. And this is the third time we're doing it, so the answer is our third derivative. So if we bring negative 2 out again, we have negative 8 e to the negative 2x. So that would be our third derivative. And really all we did was we brought negative 2 out to the front 3 times. And since it's multiplication, repeated multiplication is a shorthand for that in math is power. So this is like negative 2 cubed in the front. All right, very last thing in this section. I promise I will stop after that. And this doesn't really have to do with product rule or quotient rule, but we're going to start seeing some applications with derivatives. Now that we're understanding how to find derivatives, we know that derivative tells us slope, so we want to start thinking back a little bit to what kinds of things we did with slope in algebra class. So one of the phrases we used to describe slope in algebra class was rate of change. So for right now, we've been taking a lot of derivatives, and we've already talked about anytime you see a problem that talks about slope, you should think derivative and vice versa. And then with these application problems, these word problems, you also are going to see rate of change. And in particular, an instantaneous rate of change. And I know I have said that phrase before, but from algebra class, we used rate of change to describe slope before. I want to examine a problem in particular, or at least what exactly the derivative notation means, because it does have a meaning and it's very important to understand what that meaning is. And it will help you out tremendously when you do a problem. So if you're told that R of t represents the growth, no, R of t represents population of rabbits, let's say, at time t. R of t represents population of rabbits at time t. So that's what we're looking at. So when we take the derivative, one way we can write it is dr dt. You're always going to see the dependent variable in the numerator. The dependent variable is your output variable. And you'll always see your independent variable in the denominator. That is our input variable. So what this derivative notation means is a rate of change. It's how the number of rabbits is changing over time. So dr means the change in rabbits, and then over the change in time. So it's when you do these application problems, it's really important to understand what this derivative notation means, because the application problems are always going to be written out in words. They're not going to give you the math symbols, and you're not going to be able to recognize the math symbols and know what math operations you have to do. You're going to have to be able to read the words here and be able to translate those into math operations. So the change in rabbit population over time, if you know R of t represents rabbit population, then change in rabbit population is derivative. Derivative always represents change. So it can be an instantaneous rate of change, which is derivative, or it can be an average rate of change. If it's average rate of change, then we'll just use the slope formula. That means all we care about is comparing the beginning to the ending. So they'll usually give you an interval. They'll say find average rate of change on A to B. So that would be like an interval for your independent variable. So we would just do f of b minus f of a all over b minus a. We're not really analyzing what's happening during the time period in between a and b. We're just comparing where we started and where we ended. And that's just the algebra slope formula. The only thing different is we're using function notation instead of the y notation. That is average rate of change. Instantaneous rate of change is the derivative. And typically when you see a word problem in math class, or in calculus class in particular, and they talk about change over time, or change with respect to any other parameter that could be written as a variable, they're typically talking about derivative. Okay, so that's really important to understand that when you see the word change, we're also talking about derivatives. So a lot of the word problems we've been seeing have just been talking about finding slopes and finding equations for tangent lines, but some of the more involved word problems and the more real-life application problems are going to start using the word change, and change also means derivative.